Welcome students. In today's video we'll be talking about particle detectors. Let's go ahead and see what these particle detectors are. So these are basically devices which are used to detect energetic particles and radiations emitted during nuclear reactions and processes. For example, they can detect particles and radiations emitted by radioactive sources, etc. So these are what are known as particle detectors, and in some books they name it as radiation detectors. So both of them can be used analogously. And also these devices can be used to characterize the type of radiations being emitted by a source. That is the type of particles and radiations being emitted, the rate at which it is emitted, and the energy of emission. So they can also be used apart from detecting to characterize the type of radiations. And it's mostly based on the principle of the interaction with matter. For example, when we were talking about radioactivity, we talked about alpha emission, beta emission, gamma emission, and these particles and radiations, when they pass through matter, they interact with it. So most of the detectors are based on the principle of interaction of these particles, energetic particles and radiations with matter. So based on that, different types of detectors have been designed which can detect different kinds of particles and radiations. So they are classified based on the principle of operation and the signal produced by the detector. It can be either electrical or optical. In the case of electrical detectors, what happens is the final signal that is produced is in the form of a electrical impulse or a pulse. Current pulse is produced which is detected. Optical is something which is visible signal is produced. So they can be broadly classified into two types, electrical or optical. So basically for our part of the syllabus we will be talking about electrical detectors. So detectors can be of different types, as I told you. The one that we see here is a GM counter. It can be as small as this a tabletop detector, or it can be as huge as this. In Mexico, this is high altitude water Cherenkov observatory. What happens here is these are huge tanks containing water, and gamma rays from gamma rays which are coming from the outer cosmos, the cosmic rays, as a part of the cosmic rays we are talking about, they can be detected inside these detectors. The detailed principle we'll be not talking about here, but what I mean to show is that detectors can be as small as this or it can be as large as this. So different kinds of detectors are designed depending upon the purpose and the particles that needs to be detected. So basically we'll be talking about, first we'll be talking about gas field detectors. So these detectors are based on the phenomenon of ionization produced in a gas when an energetic particle passes through it. So this we know, when an energetic particle passes through a gas, it causes ionization. Ionization means it's the process in which electrons are knocked off from the orbits, from their orbits in atoms, atomic orbits, when an energetic particle passes through it. So what happens, the particle or the radiation, it transfers its energy to the electrons. The electron bond is broken and it becomes free. So this is the process of ionization, and most of the gas field detectors are based on the principle of ionization produced in a gas when an energetic particle or radiation passes through it. So this is the basic theme of a gas field detector. What happens is there are two electrodes. In this case, this is the anode, which is in the form of a wire, and this is a metallic chamber which is serves as the cathode. So between the anode and the cathode, a high voltage is applied. So when no particle, and usually this chamber or the detector is filled with air or other gas. Now if no particle is incident, no current will flow, so there is no current in the circuit. But then when an energetic particle is incident in the gas inside, it causes ionization, electron ion pairs are produced, so the electrons will be attracted to the anode and the ions will start moving towards the cathode. So what happens? A discharge takes place and a current flows in the circuit, which can be amplified and measured. So this is the basic principle of operation of a gas field detector. So we'll be talking about two kinds of gas field detectors in this semester, the ionization chamber and the Geiger-Müller counter. The basic difference between these two detectors is in their construction and the voltage of operations, means the voltage that is applied between the anode and the cathode. So first we'll discuss about the ionization chamber. So this is a gas field detector, as I have already told you. It's based on the principle of ionization, which can be direct or indirect. Direct or indirect means when ionization is caused directly by the incident particle or radiation. This is direct ionization, and in some cases suppose an energetic gamma ray it comes and enters the ionization chamber, it can break down into an electron and a position pair. So these electrons can cause secondary ionization, so that is indirect ionization. Or other way around, if the voltage applied is very high between the anode and the cathode, the particle it produces an initial ionization. The electrons and ions that are produced, they are attracted by the electrodes and they attain kinetic energy, and they also can cause secondary ionization. So basically, basic idea is that in an ionization chamber, it's based on the principle of ionization produced in the gas when a particle is incident in the detector. So the number of ion pairs, or rather the electron ion pairs produced, it gives information about the nature as also the energy of the incident particles and radiations. So the number of ion pairs, electron ion pairs produced, it depends upon the energy of the incident particle. Why? Because more the energy of the incident particle, more will be the electron ion pairs produced, and hence greater will be the strength of the pulse, current pulse produced. So these ionization chambers can be used to detect and measure particles and radiations like beta particles, X-rays and gamma rays. So let's look into the construction. So these are two schematic diagrams of the construction of an ionization chamber. Depending upon the purpose, depending upon the type of particle that needs to be detected, the construction may vary. Two types of ionization chambers are usually used. One is the parallel electrode, parallel plates. These are two plates which are connected to a high potential difference and closed in a chamber with a window through which the particles can be incident. This is a parallel plate kind of an ionization chamber, and in this case what happens, the anode is in the form of a thin wire and the cathode is the whole chamber, cylindrical chamber. So these are two kinds of detectors, ionization chambers, which are used. In this case, it is in the first case it's continuous current type. Current flows continuously, the signal that is produced. In this, with the capacitor, it's a pulse type. A pulse is produced, current pulse is produced. So depending on the purpose, either of these two types of ionization chambers can be used. But basically the idea is that two electrodes are there, which is enclosed in a metallic chamber, which is filled with either air or any other gas. And when the particle is incident in the medium, ionization is produced. So electron and ion pairs are produced which move in opposite directions because of the applied potential difference. So it consists of an evacuated metallic chamber with two electrodes and is filled with a gas, normally air. Also other gases like helium, neon, etc. are used. Helium and neon, these are inert gases. We don't want any corrosion or anything inside the chamber, so we use inert gases which are very less reactive or which has zero reactivity. Different designs are there depending on the use. As I told you, a potential difference of several hundreds of volts is applied between the two electrodes. So what is the working? It's nothing simple. The energetic particles enters the chamber, it causes ionization and it creates electron-ion pairs. So these ions and electrons are attracted by electrodes, leading to the generation of an ionization current, which is measured by the electrometer circuit. So the ionization current produced is very less. So what is done? It is amplified and is measured. Electronic circuitry is there. The measured current, it depends on the number of ions and electrons created, which is then dependent on the energy of the incident radiation. Higher the energy of the incident radiation, more will be the number of ions and electrons produced, and hence more will be the current. The ionization currents produced are quite small. It's 10 to the power minus 12 to 10 to the power minus 15 amperes. For example, the minimum energy required to produce a pair of electron ion in air is around 35 electron volt. In an air-filled ionization chamber, a 3.5 mega electron volt alpha particle can therefore produce 10 to the power 5 ion pairs. So this is a typical value of energy of an alpha particle emitted by alpha particle source, 3.5 MeV. So in air-filled ionization chamber, it can produce around 10 to the power 5 ion pairs. So a source emitting 10 to the power 4 alpha particles per second will produce a current of around 1.6 into 10 to the power minus 10 amperes of current. So per second, if the alpha particle source is emitting 10 to the power 4 alpha particles, the current produced will be only to 1.6 into 10 to the power minus 10 ampere. So this is very less amount of current. So this is the characteristic of an ionization chamber, voltage and the ionization current. Initially, as the voltage is increased, what happens? The ionization current increases. Why? Because when zero voltage means electron ions pair, even if it is produced, it won't reach the electrodes, so there will be no ionization current in the circuit. As the voltage is increased, the electrons and ions, they get attracted by the electrodes and a current is produced. Higher the voltage, more the current. So the ionization current, it increases with the increasing voltage. But beyond a point, what happens? If the voltage is higher than U1, then all the ions and electrons are reaching the electrodes. So from U1 to U2, all the electrons and ions are reaching. So even if the voltage is increased beyond U1, the number of electrons ions produced remains constant, and hence the current also remains constant. Higher voltage doesn't lead to more number of ions and electrons reaching the electrodes, because in the voltage region of operation of an ionization chamber, there is no secondary ionization produced. But when the voltage increases beyond U2, what happens? The electrons and ions, as they are getting accelerated towards the electrodes, as they are moving towards the electrodes, they gain energy because of the applied potential difference. So what happens? They gain sufficient energy to cause secondary ionization. Again, the current starts increasing. So for the ionization chamber, the voltage is kept in this region where there is no secondary ionization. For a higher voltages, the other detectors, one is there the proportional counter and the Geiger-Müller counter, they operate in higher voltages. We'll discuss about it later. But for the ionization chamber, what happens? It is allowed to operate in regions where secondary ionization is not there. So this is a characteristic of the ionization chamber. So let's look into some advantages and disadvantages of the ionization chamber. It can be used for activity measurement as well as dose measurement. Means we can check out the number of particles that are being emitted by a source, that is the dose measurement, and the rate at which it is emitted. So an ionization chamber can be used for activity measurement as well as dose measurement. No inherent amplification of the signal and hence have faster recovery rates. Inherent amplification of signal means there is no secondary ionization produced. So whatever pulse is being produced in the ionization chamber is because of the energy of the incident particles and radiations. And hence, as because no secondary ionization is there, the chamber gets ready to detect the next incident particle faster. That is what we call as the recovery rate. It can be used in current mode or pulse mode. This is about the signal we talked about when we talked about the construction of the ionization chamber. It can be used in both current mode or pulse mode. Means the signal produced can be in the form of a continuous current or in the form of a pulse. So that's all about the ionization chamber. So next we'll be talking about the Geiger-Müller counter.